In the world of artificial intelligence, few breakthroughs have sparked as much excitement and debate as the emergence of large language models. These systems, capable of generating human-like text, answering complex questions, and even writing code, are no longer just the domain of tech giants. They're reshaping how we think about language, cognition, and the very nature of intelligence. But how do they actually work? What's going on under the hood when you type a prompt and get back a response that feels eerily coherent? Let's dive deep, not just into what these models do, but how they learn, how they reason, and why their behavior can sometimes seem both brilliant and bizarre. At the heart of every large language model is a neural network, a vast web of interconnected artificial neurons inspired by the human brain. But unlike biological neurons, these are mathematical functions that process data through layers of abstraction. The most powerful models today are based on the transformer architecture, introduced in 2017 by Vaswani et al. In the paper, attention is all you need. This innovation replaced older recurrent models with a new way of processing sequences, by focusing on relationships between all words in a sentence simultaneously, not one at a time. This is where attention mechanisms come in. Imagine you're reading a sentence. The cat sat on the mat which was red. When the model processes which, it doesn't just look at the previous word, it uses attention to weigh how relevant each word in the sentence is to understanding which. It might assign high attention to mat, because the color is describing the mat. This dynamic weighting allows the model to capture long-range dependencies with astonishing efficiency. The transformer architecture is built on two key components, the encoder and the decoder. In models like BERT, only the encoder is used, ideal for understanding tasks like question answering or sentiment analysis. But for generative models like GPT, the decoder is critical. It generates text one token at a time, predicting the next word based on everything that came before, using attention to focus on the most relevant context. Now here's where it gets truly fascinating. These models aren't trained to memorize facts. They're trained to predict the next word in a sequence. That's it. Given a massive corpus of text, books, articles, websites, code, models learn statistical patterns across billions of examples. They don't understand meaning in the way humans do. They don't know that Paris is the capital of France. But they've seen the phrase Paris is the capital of France so many times that when prompted with, "What is the capital of France?" they predict Paris with high confidence. This is called autoregressive generation. The model starts with a prompt, generates a word, then feeds that word back in as input to generate the next one, iteratively building a full response. Each prediction is based on the probability distribution over the entire vocabulary, shaped by training data. The model doesn't decide what to say. It calculates the most likely continuation given what it's seen before. But how do they avoid repetition? How do they stay on topic? That's where temperature and sampling strategies come in. Temperature controls randomness in predictions. A low temperature makes the model more deterministic, favors high-probability words, leading to safe but predictable output. A high temperature introduces more randomness, encouraging creativity but risking incoherence. Techniques like top K sampling or nucleus sampling, top P, further refine this by limiting the pool of possible next words to only the most plausible ones, balancing coherence and diversity. Now let's talk about scale. The performance of these models doesn't just improve incrementally with more data. It scales in a surprisingly predictable way. As you increase the number of parameters, those adjustable weights in the network, the model's ability to generalize, reason, and handle complex tasks increases dramatically. This phenomenon, known as scaling laws, shows that bigger models aren't just better, they're fundamentally different in their capabilities. But scale alone isn't enough. The quality of training data is equally crucial. Models trained on diverse, high-quality text perform better. They learn more nuanced language, avoid biases, and generate more accurate ethical responses. That's why datasets like Common Crawl, the Pile, and curated academic corpora are so valuable. And yet, even with the best data, models inherit the biases, errors, and contradictions of the human world. This leads to a critical point. Large language models don't know anything. They simulate understanding. They're statistical engines that have learned to mimic the patterns of human language. When a model says, "I don't know," it's not expressing uncertainty. It's predicting that the next word is more likely to be, "I don't know," than any other phrase in its training data. So what does this mean for the future? These models are not conscious. They are not agents. They are tools, powerful, flexible, and deeply capable, but tools nonetheless. They can assist in research, help write code, summarize documents, and even generate creative content. But they don't have intentions, beliefs, or desires. Still, their emergent behaviors are astonishing. Some models can perform multi-step reasoning, solve math problems by breaking them down, or even write programs that execute correctly. These aren't features explicitly programmed in. They emerge from the sheer scale and complexity of the training process. And that's the paradox. The more we learn about how these models work, the more we realize that we don't fully understand them. We can trace the math, analyze the attention patterns, measure performance, but the why behind their sudden insights remains elusive. This is not a flaw. It's a feature of complex systems. Like ecosystems or economies, large language models are emergent phenomena. Their intelligence isn't in any single layer or parameter. It's in the collective behavior of millions of interconnected parts. So as we continue to push the boundaries of what these models can do, we must also ask deeper questions. How do we align them with human values? How do we make them more transparent, reliable, and fair? And perhaps most importantly, what does it mean for us as humans to coexist with systems that can write like us, reason like us, and sometimes even surprise us? The answer isn't in building smarter models. It's in building better understanding of the technology, of ourselves, and of the future we're shaping together.